This is lecture number 19. In this lecture, we will be talking about distributed file system being created through peer-to-peer mechanism. So the basic of how the DFS will be created was discussed in the earlier lecture. But for a distributed file system, we need storage space. So in the earlier lecture, there was an assumption that all nodes will be contributing the storage space equally, but that is actually not true. Sometimes it is possible that a node is there, but it is not going to have a sufficient amount of storage space. So what should happen in that case? How to handle this kind of situation? So the technique which I will be describing here is very specific to Brihaspati 4 system. So we actually create a storage space, a storage DHT. So all the nodes which are contributing the storage, they form their own DHT network, and we call it a storage DHT. So this is another layer which gets formed in the multi-layer DHT system of Brihaspati 4. So we actually solve the problem of storage, but the people who contribute to storage need to get some incentive. So we will also be talking about the incentive mechanism. So that people are encouraged to contribute the storage, they should get something in lieu of that. So idea works in this fashion that if you contribute more storage space to the community, the more storage will be provided to your file system by the community. So if you contribute less, you will get a less share out of the total cooperatively created storage system. So let's see how this actually can be done. So if there is no storage DHT and there are nodes which are participating, so what can happen in this case? So most likely what will happen is everybody is now creating a file system. So they will be making DFS, a kind of key values will be in this fashion. There will be email. This is the same way as I had discussed earlier. And then of course directory, subdirectory, file name. And then of course this will be creating, when you search for this key, you will get a descriptor file, and from there you will get the multiple fragments, and each fragment's hash ID, hash of the content will be there, and we will use this hash to search for where the file actually is going to be there, and we will have then copy 1, copy 2, copy 3 of each one of them getting created. But since all these when we are computing hash IDs, they will be all uniformly distributed in the whole hash ID space, and since these nodes are also uniformly distributed, so everybody is supposed to get almost same kind of storage requirement. Each fragment is of fixed size, say 512 kilobyte or 1000 kilobyte, 24 kilobyte. So everybody will get the same share of storage requirement. So everybody should equally contribute. If all machines are of equal capacity, then of course there is not much of an issue. But since we don't expect everybody to be of equal capacity, then what has to be done? So somebody is having a very lower storage space, say having 100 GB only. Somebody provides 1 terabyte. Somebody is going to have 500 terabyte. So how we will handle this kind of situation? So one possibility is that the hash IDs for which a node is responsible. Okay. So number of hash IDs in this area for which this node is responsible, this volume of the hash ID space which is closest to this, or for which this is a root node, that we can differentiate that actually. But will that be feasible? So, or if you look into the CORD system, so all the nodes are equally spaced almost statistically. So what I am telling is, for only some very few entry, because this has a lower storage space, very few entry should come here. So I am saying that this node should be closer to this previous node, so that very few entries will only be stored here. Okay, so their spacing has to be dynamically adjusted such that the different amount of key value pairs, or basically file fragments, different amount of file fragments will be stored at different nodes, which are going to be matching with their whatever storage which they can provide. But that actually is not feasible. Reason being because node IDs are not being, cannot be explicitly configured. They are always randomly generated. We did that so that we can actually avoid denial of service attack. Okay, this we had covered in one of the earlier lectures. So we wanted to take care of this. That's why we actually started with a random generation. We started that node ID will be the public key, and the corresponding private key and this public key will be generated together. So this can only happen through a random generation process, and this private key will be used to sign this one so that we can prove it is indeed generated through the same process, and because of which it's a random key. And this private key is always maintained at the node so that it can actually, for anything where node ID has to be proven to be held by that node, can be proved by this private key. So this mechanism whereby I can actually have different amount of hash IDs being routed at one particular node depending on the storage actually is not feasible in Brihaspati 4 system. So we have to do away with that. So what could be the alternative? If we cannot do this, we need to have an alternative approach. So the question is, if a node does not have a sufficient space, what it's going to do? Okay. So if a node does not have sufficient space, what should be done? So one thing what we do is, because not everybody is going to have the storage space, so we create the nodes which can provide want to participate in storage system. They will actually now create a separate layer, separate DST layer, and those node IDs will have their own routing table. So only the neighborhoods in this people in this set of nodes which are participating in providing a storage service. So this node will actually maintain routing table to the nodes which are present in this particular layer. Of course, base layer will also be present, but base layer mostly will look into user ID to certificate or user ID to node ID mapping. So those will be maintained by the base layer. But similarly, we will have this layer also storage, but this now will be providing a storage. So anything which have to do with the file system, like this, the file fragments, so a universal file system part where the content hash ID, content hash will be used to find out the content, and of course using this key which is a in file namespace of a specific user, a specific file pointer, based on that finding out its descriptor, and then of course the file fragments and to retrieve them. So all these particular data will be kept in this storage DST. Now in this case it is possible that some node may not have sufficient space. They have contributed, this guy has only contributed say 100 GB and it gets filled up. So normally everybody will get equally filled up as the storage comes into use, because even if you put up a one single 1 GB file, it will get fragmented and it will be scattered around across the whole storage DST. So statistically everybody will be filling up at the same rate. So but the guy who has got the lowest, so this 100 GB is the lowest storage, so this will get filled up first. Now what to do in this case? So there will still be requests which will be coming here, so where they need to go. So we actually devised a new mechanism, we call it a spillover table. Okay. So there will be hash IDs which will go and then route it through DST and which will go to a root node. So once the key value pair, the query actually reaches here or a publish request reaches here, this guy says I don't have the sufficient space, what has to be done? So it will now actually look into its own routing table of this particular storage DST layer, and will actually now send a query to various nodes which are listed and asking them that I am running short of space, can anybody is willing to give me the space. Now that's where this, currently let's assume that everybody is willing to contribute and sort out the issue. Nobody is doing free riding, so nobody, R is not actually doing cheating. It actually has always the filled up space. So everybody is honest, let's assume that. Later on we will come to the reputation mechanism by which there is no incentive in actually doing the cheating. So that's basically the algorithm which is specific to our system. So once these actually extra nodes are find out, we call them proxy route, because they will be actually acting as a proxy route for the entries which are supposed to be held by this root node. Okay. So they will act as a proxy there. And let's see what's going to happen in this case. So now this node, root node, whenever the query will come, we'll have to now keep track whether the key value pair is with me or with a proxy route. Okay. Now which proxy route is going to have it? So at this point it is going to be through routing tables created through DHT network. Through that the routing will happen. Once it reaches the root, after that the routing will be happening through something called spillover table. Because the space has been filled, now the query is being spilled over to place to a node which is having the space. Okay. So for every, now the question is for which all key value pair it should put the values here. Okay, all the requests which are terminating at root has to be, need not go here. Some of them will be there in the current indexing table or key value pairs in indexing in the storage locally, and remaining has to be put there. But how that will be done? So we have to find out this root node is responsible for which all hash IDs. Okay, for which all hash IDs it is responsible. So in fact, for any DHT network, when R is sitting there, R actually, depending on, by looking at its routing table, it can actually figure out for which all hash IDs it is a root node. Now question is, this hash IDs for which this is going to be root node, whether they are contiguous or not. So in CORD, if you look, the CORD table if you make, so if you have nodes here, so you can see this is a contiguous block for which this is the root node. This is a contiguous block for which this is the root node. So this is never fragmented. So I actually can know now when I don't have a space, I have some other proxy route, so I can find out P1, P2, P3 depending on whatever is the requirement. In fact, it should send the message and some people will come back and they will say this is the storage which I can provide, this is what I can provide. So R will have now in this protocol will know that which all are providing, how much I have, and based on that this hash ID range has to be partitioned. This contiguous range, this is the range, depending on how much storage is there with whom. Okay, it will say okay, this much I am going to keep, this much the first P1 will be keeping, this is the second P1, P2 will be keeping, and so on. So it will do a split. Now what it will do is it will now create a spillover table entry. So for this range, it will now specify this range. For this range, you have to do a local search. For this particular second range, you should move to host P1. So there will be P1's node ID can be there or P1's IP address and port number can be there. Node ID is also fine. In that case, destination address will not be hash ID but will become P1. The node ID will be their destination address, that replacement will be done in the query. Query will move here and P1 knows the query has come to me, and then it's going to essentially look into this whether I am the root node or not, or whether the entry is there in my spillover table. Okay. So once the query goes to P1, so P1 will also have similarly a table. It will say that for which particular entries its own spillover table will be there. It will say for these entries which are in my range, look into my storage. Then it will say if it is actually providing storage to others, normally we expect it there is no spillover table, so it is able to take care of all its own entries first. So there is always a rule that you should always take care of all your entries first, then only give the space to others. If you are running short, you simply tell the other root node for which you were taking care that you don't have the space, and you will find out some other people where it can be rerouted. So that procedure has to be done. So, and then of course, if there can be now entries from the remote side which can come, and it will say that I am actually maintaining entries for these for which I am not root, and these entries are there with me, it's not with somebody else. So there may be sometimes feasible that it's coming to you, you are running short of space, you have told him but you have to keep the entries, You can actually make a mechanism whereby even you can further do another spillover and go to another root node. You are not storing it, but then that's very inefficient actually. So in Brihaspati 4 we have not implemented that scenario. So it can go at most to only one, what we call proxy root. Okay, is also acting as a proxy of this particular root. That's why we call it a proxy root node. So only one step you should be able to go there. Okay, so and anybody who is maintaining this table, either you will be having it or you won't be having it. If you don't have any entry, you will just respond back to the source that entry is not available. Okay, and I am sending it on behalf of this particular R. So, and if R does not have the entry, it checks with the proxy root. If the range is telling that this particular key ID range or hash ID range has to be with the other some other guy, he will look at the entry. If he does not have the entry, he will simply say I don't have the entry, or he will actually have the entry, he will pass on the entry. Now the source will be knowing that who has given me the entry. So he will figure out that P1 actually has given me the entry, not the R. Now that is very important because P1 has to be given a credit for storing the thing, not the R. So that will be required for our reputation system. Now briefly coming back to this contiguity is there in CORD. This is guaranteed. In Pastry this happens. Even in Kademlia also this happens. We actually can verify this happens in Kademlia. So for example, you check, you will have, you put some nodes there. I can try, for example, I have 1001. I am going to put 0010. I can put node say 1101. Then I can put 0001. So let these be the Kademlia nodes. So for which entries these will be responsible. So I can actually now find out basically XOR distance for all hash IDs which are feasible and see with whom they are closest. And then look at that range. So this range will always be contiguous. So, and this is of course is obvious. So for example, look here. So this is for Kademlia I am doing it. Similarly for Pastry Tapestry it is of course obvious because it's going to be on a circle. So this whole range, this is going to be the root in case of CORD. Okay. For Pastry, if you have a node here, okay, so this half of this whole range, this will be the root node for that. So this will also be a contiguous block. Kademlia we can now verify it here. So if I start with all zeros, so all zero when I do, I will just look at the which is the longest match. So all zeros matches with this one. So 001 it's here only. Okay. So I am just going to do this longest match business, and with that I can find out who is going to be a root node. And then of course 0010, so that will come here. 0011, so this will also come here. You can actually see I will not be coming back here again. Okay, now 0100, 0100 will be matching closely here. So then 01, and you can actually now understand why this is happening. It's a basically longest match thing because of that. 101, 0110, 0111. Okay, now next entry will be 1000. So this will be having longest match here. So now I won't be going back to this. Okay, this is the longest, this is a contiguous block which is there. This is a contiguous block, this is a contiguous block, and including these at this entry also. Okay, you can actually, this entry is going to be there. So remember, this entry is nothing but the same thing. Okay, zero distance. So then 1001, so which is same. So 1010. Okay, so this is going to be 1010 will also be coming here only because this is the only entry left. Then 1011. The moment I say 1100, then this is not the match, it will be this 1100. So this entry is done, and then 1101, 1110, 1111. So all are contiguous blocks. Now this is not true in case if we are using Tapestry. So for Brihaspati it is not true actually. So Brihaspati we are using a Tapestry algorithm technically, but our routing tables are smaller in size because we use kind of a CORD kind of arrangement on in every column. This we had discussed earlier in one of the lectures. So if we try doing this on say tapestry kind of thing. So let me take a node A, B, C, D. Okay, so I am taking a 4 nibbles, 4 hexadecimal number, only 4 digit node ID. So let's look at the first thing. So what entries I am going to have. So if I have entries say B 0, so this is the entry, the way is going to be there in Brihaspati 3 tapestry chord hybrid, actually I should call it. And then of course the next entry will be anything which is going to be midway. So this can be say 5112. So I am keeping something arbitrary. Then 9215. Then obviously after that, between 9 and A, whatever is going to be there for that A, B, C, D's or any node which is starting with A will be responsible. So anything which starts with, after 9 we get 10. So there is only A, the entries which will be present. Okay. So only for nodes which are starting with A, this will be responsible. I have to go to the second column in this case now. The second column I am just taking slightly differently. I am taking AC 20. I am not bothered about the middle value, it does not matter. But here I am actually taking a different value. I am taking 8. So there is A9, AA and AB, for which now this range will be AB range, ABXX will be responsible, domain will be responsible. So I have just taken intentionally this particular thing. So for A9, okay, AA and AB, the nodes which are starting with this, for them actually ABCD can be the root node. Okay, for A9 and A8, somebody from ABXX has to be the root node, so ABCD is one potential candidate. So I will find out for which entries will be there. So next let's look at the third column. In this case I am actually intentionally again putting the values in same fashion, ABE0, and then we have AB91, and I put ABCF, and here ABCD. So if I look at now, once for A9, AA, AB, I will come back here. If I am at ABCD root node and I am searching for something with A9, I will come here and I will now look at the third digit. Okay, third digit is going to be there between 9 and C. Everything has to be there. So I can now say that A9 and of course A9A, A9B and A9C, for which I will be essentially ending it over to ABC, only this particular node. Similarly for AA, A and AAB and AAC also. Okay. And similarly for this three things, so you will get ABA, ABB and ABC. So these three, and I will put XX, so my ranges have already got a split. Okay, there will be some range which is not going to be having root at ABCD, it will be having some other node, some other node will be the root node for that. Now let's look at the fourth entry. So the fourth entry will be now ABCF and ABCB. So BC and D, for which this is going to be responsible. So I can now write A9 AC, A9 AD, for which ABCD will be responsible. Okay. Similarly, I can look at this and say A9 BC, A9 BD. Again, this node will be responsible. There is a gap here now. Okay, which is left. So EF, A9 AE, A9 AF, for which this node will not be responsible, some other node will be there. So the entries are not going to be contiguous for tapestry chord hybrid. So we cannot use a simple strategy of saying, okay, whatever you find out for whom you are responsible and bifurcate that hash ID space for which you are responsible, because this hash ID space for which ABCD is responsible is not contiguous. This is actually fragmented. So some other places, this actually is going to be responsible for that. Okay, so similarly for A9C, actually you can do A9CC, A9CD. For each one of them, just we will put C and D actually. Okay, and AABC. So you can actually appreciate how this is happening and you can keep on doing it. So this is what is the hash ID ranges for which hash IDs for which ABCD will be responsible and it is not contiguous. So we actually improvise on our algorithm here. And what we do is we now use an mechanism. So there is one possibility. I can always say A9XX based hash IDs will go to node P1 and of course AAXX will go to P2. That's one way of doing it. So prefix based thing. So I know that A9XX there will be some hash IDs coming to me for which this guy gets responsible, for this one this gets responsible, but I will not be able to do a clear division. I have to find out how many are there and then each block has to be assigned to different one. I have to identify the blocks. That could be one possible way. But what we have done it in a slightly different way. So what we do is we identify what's the lowest key actually which has come so far being for publication and what's the highest key which has come for me for the publication or query. So this is what we call as a range for me and this is what is being bifurcated or trifurcated and then is being assigned to different nodes. Okay. I am assuming that there is going to be gaps which are uniform. So when I am doing a bifurcations, I am not allowing something for which I am not the root to somebody else, and of course no storage will be used there. Okay, that should not be happening. Does actually can happen, but we are living with it as of now. So if somebody's hash ID coming which is out of this range, so I will change this my pointer of the lowest to the value which is given by this. Similarly, I can update this value also depending on whatever is coming, and the range will keep on adjusting. For which I am figuring out I am the root node. So I will know what is the lowest value of for which I am root node and which is the highest value for which I am root node, and I am essentially bifurcating that space to the nodes. Okay. So in fact, we can even do a much more sophistication. We know that these are the entries, how many entries are available. Okay. And when I figure out there are more, so I will just do a midway bifurcation. I know which is the entry here, and this range is what is going to be directing to P1. This range is what is going to be there with me. And when more entries come, which is somewhere in between, then I have to allocate and I will update one of these, whether I am keeping it here or here, depending on the size. So this is the algorithm which we have been using. So these ranges are being dynamically adjusted in our case. Okay. So the rule which is followed is that every node before it will create a spillover table. So this basically spillover table creation mechanism, so where the ranges are being specified. So normally every node should keep 25% space available. So when you reach about 25%, that time you will start creating a spillover table. That time you will start a query for finding out the people who can give you the storage space in form a spillover table. Then of course query will come to you, and from there now you will have a spillover table, and based on the ranges which are defined here, you will either search locally or you will then hand it over to your proxy route. So it will maintain the key value pair and will be responding to the requester directly, the guy who has made the query. Now what this S node, this which I am actually storage node, this R node, this need to keep on republishing this entry periodically. So there has to be republish timer. So once it will do a republish, it will go to this current node always. And this in turn will always look at the spillover table and pass the things to it. If the entry already exists, it will now reset the timer. If it is a new entry, that actually means the R has now decided on some other spillover, basically depending on the consumption which is happening. Okay, if again even after this the value goes above 25%, even after this thing, it can actually now further find out more nodes, S1 and S2 now, and then actually now do a bifurcation further. The spillover table changes. So next time when you republish, it goes to new node actually. So it won't come back, and then ultimately your timer, you will keep this entry for some time. If it get refreshed, it's fine. If it does not, you will just purge it. And by the time this entry must have been placed at some other node. Okay. So this is the way it is going to be republished again and again. And of course, it also need to know whether it's if this is the copy 1 or copy 2. If it is copy 1, it will be doing a republish for a copy 2 in that case. So there will be another node sitting in here. Okay. So it will now do a republish for copy 2. So this will ultimately end up and terminating here. And this root node may not have a proxy root being defined, so it is storing locally. Okay, this also has a republish timer, so it will now do a copy 3 publication. So somebody will be doing a copy 1 publication, which will come here and which in turn will get replenished here. So it's a cyclic thing. So we are doing parallel fork for resilience purpose. Okay. So the shortage of space is now taken care of in this fashion by actually borrowing the space from S1 and S2. But what S1 and S2 will get out of it? That's the question which remains. Now, in order to solve this problem of that people should not free write, so we now do, we actually also create another mechanism. We call it a reputation management system. Now, in order to ensure that nobody free writes, so people who contribute should actually get their fair share in the whole storage DST. So we need to build up a reputation management system. So there will be some nodes which will be now can build up another layer, another DST layer. We call this DST layer as reputation DST. So basically reputation is a number which goes between 0 and 1. So depending on if somebody who is going to have a higher value actually means that he is cooperating, he is actually providing access to others, he is actually giving his storage space for others to use. Somebody who is giving less storage space will have a lesser reputation system. So higher the storage which you contribute, the higher the reputation you will have. Lower you contribute, lower you will have. And accordingly you will end up in also getting your share in the total storage which is being provided by the DST network. So there will be only some nodes, roughly 10% of the nodes will be good enough, because each node then has to maintain on an average the reputation of 10 other nodes. And this is of course through hashing. So whatever is your node ID, so we will just compute the hashing of this. In fact, we have to do some more trick, because a single user might actually end up in having multiple devices, okay, which each one of them will have a different node ID and which are putting in the space together. So when actually trying, whenever some file which is going to come for storage, it is going to come from a user ID, not from node. So we have to now search for this user ID, what all node IDs are actually assigned to it. We have to compute their reputation thing, and based on that their reputation which we have, okay, basically how much storage they are actually pumping in, that will decide essentially the reputation. So higher storage means higher reputation, lower means lower. Then we can compute an average of this, and that average can be used to compute that how much, whether the file which is being published by user ID has to be, or the fragment has to be stored or not stored at a node. Okay. So the logically the way it's going to happen is, whenever a user trying to find out a fragment, it will access, it will go to the root node, it will then go to through spillover table will go to the storage node, and storage node will supply the file back to him. Once the file comes to him, it will simply then inform for this S, this node ID, there will be somebody who will be a reputation server. So it will just compute the hash of it, and this will be routed in DST layer. Basically there will be another routing table corresponding to this reputation DST. So this this particular message will be going towards somebody who is going to be a reputation server for S1. So the moment this guy gets, this will and we will also limit that how many it can send, how many it will, every time it will send one, it will just send a signal. I asked for a fragment, I got the fragment, and it can only send every 15 minutes say one. That's what we have been keeping. So he is actually accessing a lot of files, only one entry will be going, and then of course it will be maintaining a cache memory also. So next time it won't be accessing, it will be only fetching it from the cache. Okay, local cache every node is supposed to maintain, as I have discussed in the previous lecture. And this one, whenever it comes here, so there is going to be an older reputation value which might have been taken at say some value t minus tau. So t is the current time. So this value we will decay it by, because whatever is there in time, the reputation should go down. If there is nobody's accessing the from S1 is not providing file, earlier it has a very high reputation value, it should decay actually. So we will define e raised power minus alpha tau as the decaying function. So alpha is roughly kept in such a way that within 24 hours this value comes down to 0.1. Okay, so we will have some alpha tau value this is what is going to be the coefficient by which will become weight of the older value plus the new value which has come is 1. I will also keep the weight 1, and then I will do the weighted averaging. So this will be my new value at t reputation. So if there are many nodes which are actually trying to access the file fragments and S1 is providing, so a lot of ones will be coming here to same thing, and this RT will keep on replenishing. This value will remain very high actually if it is providing service. If somebody is not contributing, it will be low. So alpha essentially has to be chosen in such a way that the value is going to be somewhere in between 0 and 1 midweight. All values should not be skewed. The distribution of the values at any point of time should not be something like this. Ideally the value should have a distribution which is going to be something like this actually. So this alpha has to be chosen in that manner. So this needs some study. So through experimentation we will figure out how much alpha will be required. So it all depends at at what rate people will be accessing the files. Normally caching will be there. When you don't find anything cached, then only you will get it. Okay, so sometimes you may not be running the application, you are not accessing it, so only part of the nodes from the whole network will be accessing the file fragments from S1. Okay, but the question is, the guy who is contributing higher storage will be accessed more by more people, so he will have higher RT value at any point of time compared to anybody else who is providing less storage. Okay, so once this is done, so storage is going to be for S1 node will be updated. Now S1 want to publish something, what is going to happen? So how the advantage comes? So S1 will now give a publish message. Now this goes to some guy who is a root node. Now root node figures out, okay, then I need to publish it. It does not have that much storage space. Okay, so it actually can have somebody who is providing the storage thing, so it may call SP, and the request goes here. So this SP will say, okay, I am supposed to publish for S1. There is a key value, and normally remember all fragments are of equal size. That's what we have been maintaining in our design. So SP will now search, again make a query to the reputation server of S1. So query will go here, and S1 will provide it back the reputation value. Now SP will simply do, it will find out what's the occupancy as of now, occupied storage, divide by the total storage which is available. So this, if this value is going to be smaller than the reputation of S1, then the value will be stored, otherwise it will be declined. It will be simply sent back to R, and R has to find out somebody with having more space, which is going to have less fractional utilization. So utilized space, that fraction should be lower, so it has to go to only those nodes. Okay, so R actually can keep various different nodes and can find out what are the fractional values which they have. But in that case, the problem is this, R has to have that spillover table has to be modified. But normally it is not required. Simply there should be a refusal which should go back. So S1 cannot store more than a certain value. So it has to essentially now contribute more storage to make its RS very, very high. So the higher the contribution it has, the chances are that anybody who is having this value will actually store it. Intuitively, we can actually see that most likely, but this still needs a verification. So we are investigating this particular part, that almost everybody's fractional utilization will generally tend to be same in such a scenario. Okay. So anybody who is going to have a lower reputation will be discarded. Only in the beginning they might be able to store, but after some time when everybody's storage will start building up, they will not be able to store their files. In that case, they will get denied. So some fragments will get stored, some will not get. But normally this is going to actually use copy 1, copy 2, copy 3. So they will, it can actually will find out only certain copies it's able to store, not the others. Okay. And this problem is going to be there. So one possibility is might is reduce the storage. Copies can try randomly, and in some random trials it will find out that the storage is available, sometimes it will not be. But most likely, since it's a feedback system, so higher you contribute, the chances are that you will have higher reputation, chances are that other people will be able to store you. Okay, so there is a, you get an award for actually sharing a higher storage space, and you will get a higher chance of getting your files stored. If you are sharing less, you have less chances. So this automatically gives an incentive that you tend to contribute more towards the storage so that the other people will do it. Now, one of the problem here is the people who are not participating in storage DHT. Okay, they want to actually use this, have a DFS and want to use the storage, they cannot actually. Because they are not contributing anything, their reputation will be zero as far as the DHT layer for the reputation is concerned. So in such a scenario, probably there has to be, we have to build up some mechanisms through which it can actually buy the space. So in that case, a node ID, if it gets into a contract and node ID provides, okay, I am going to contribute space on your behalf. So then actually for this user ID, I can now store user ID to node ID publication when it has to be done. So even this node ID has to be added there. Okay, so this node ID will actually now allow this node ID to be added. Okay, and what happens is normally this user ID cannot arbitrarily put anybody's node ID here. Okay, it has to be signed by this entry has to be signed by the node ID's private key as well as the user ID's private key. Then only it will be feasible. So we have to make a change here that every user ID to node ID mapping has to be signed both by the node ID's private key as well as the user ID's private key, user's private key both. Okay, so there is an agreement that this user ID to node ID mapping is perfect. And now based on this, because this guy is providing contributing storage, so this guy gets a higher reputation and its actually files can be stored in the storage DHT. So that's the way, for example, you can actually now buy storage from the storage service providers. So that's the mechanism in peer-to-peer system which can be used. So this is what we have been planning to use for storage system. So this is how the file system will get implemented, and where the storage will also be balanced. We will also have some kind of a rudimentary reputation system. Of course, this will still need a careful analysis. But as far as by using this logic that higher you contribute, the more chances are that your files will get acceptance in the storage. This particular mechanism essentially ensures that there is a tit for tat. If you are contributing less, you will have lower reputation value and your files will also not be stored. So the free riding can be somehow taken care of in this system. So with that we end today's this video, and we also end this whole discussions on storage systems. Now we'll go to overlaid multicasting, how to essentially do broadcasting of live sessions or live lectures in a peer-to-peer system.